Hello everyone, I am Mohammad Ahmad Qureshi, working as an assistant professor in Civil Engineering Department at RNG Patel Institute of Technology, Bardoli. In our previous lecture, we had gone through seismic methods of analysis, so we will study the examples related to seismic coefficient method. In seismic coefficient method, we have to assume that the earthquake forces are static in nature and we consider only static condition means the forces are not vary with time and the seismic forces are lateral forces which acts from any orthogonal direction. So we will solve the first example related to seismic coefficient method. Here, what is given? The plan and elevation. So here, the plan and elevation of a three-story RCC school building. Of a three-story RCC school building. Remember this word, RCC school building. This parameter will help us for getting the value for importance factor. Then the intensity of dead load is given as 12 kilonewton per meter square, including columns, beams, walls, and floors are to cater an imposed load of 4 kilonewton per meter square. Live load is given as 4 kilonewton per meter square and the building is situated in zone 4. Here the building is situated in area of zone 4. So this data will help us for getting the value of zone factor from IS 1893 part 1 2002. And the type of soil encountered is medium soil. So here the soil is given as medium and this will also help us for getting the data of SA by G value, that is average response acceleration coefficient, and it is to propose the building to design with its SMRF, special moment resisting frame. So we have to determine the seismic forces and shears at each floor level using static coefficient method. So here we got the height of the building as 9 meter and here 4 meter to 4 meter means the base dimension of the building is given. So this will be your building height and this will be your base dimension of the building. So now we will go for step-by-step procedure to solve the seismic forces and shear at each level. First of all, we will note down the design parameters that are given in example. So first parameter is building is situated in zone 4. Second is dead load is 12 kilonewton per meter square. Then imposed load or live load is given as 4 kilonewton per meter square and the soil type is medium and the lateral load resisting system is given as SMRF, that is special movement resisting frame. and we will calculate the floor area. So your floor area will be 5 plus 5, that is 10, and 4 plus 4, that is 8. So your floor area will be 10 into 8 equals to 80 meter square. Now we will go for first step. Different loading conditions are given in example. So we have to calculate the total seismic weight of the building, that is capital W. So first of all, in first step, we will write lumped masses to various floor levels. In that, your first case is dead load. The intensity of dead load is given as 12 kilonewton per meter square, including slab, beams, columns. So your dead load will be equals to 12 kilonewton per meter square. Now we have the floor area as 80 meter square. So we will first go for typical floor, that is weight of typical floor equals to floor area, that is 80 into dead load 12. So you will get 960 kilo Newton. Now second parameter is weight of roof. So again your floor area is 80 into dead load is 12. So the weight of roof will be 960 kilo Newton. So we get the data for typical floor as well as for roof for dead load 12 kilonewton per meter square. Now we will go for live load. So our second step will be live load or imposed load. Live load can be calculated as per IS 1893 Part 1 2002 page 24 table number 8 that we had discussed in the previous lecture. So the earthquake force shall be calculated for full dead load plus the percentage of live load. So here first case will be the imposed load or live load on the roof need not to be considered. We had seen in our first lecture. It is given in IS code and the clause number is 7.3.2. So live load on roof will be 0, and now we will calculate live load on each floor. So for calculating the live load on particular floor, we will go for IS 1893 Part 1, 2002, page number 24, table 8. So, in this clause, it is given that for live load greater than 3 kilonewton per meter square, 50% of the live load is to be considered. And in our case, means in given data, we have the value of live load as 4 kilonewton per meter square. So 4 will be greater than 3 kilonewton per meter square. So we have to consider 50% of the live load. So your live load will be equals to 0.50 into 4, which will be equals to 2 kilonewton per meter square. Therefore, total live load on each floor will be equals to floor area, that is 80 into live load 2. So you will get 160 kilo Newton. So on each floor your live load is 160 kilonewton. On roof it is 0. Now we want total seismic weight of the building. So our next step will be lumped mass of roof equals to dead load plus live load. Here we had calculated the value of roof as 960 kilo Newton, and for roof live load is 0. So here lump mass of roof equals to 960 plus 0 equals to 960 kilo Newton. So we get the lump mass for roof as 960 kilo Newton. Now our next step will be lumped mass of each floor will be equals to dead load plus live load. So for each floor we get the data in case of dead load as 960 kilonewton, and in case of live load we get 160 kilonewton. So here lumped mass of each floor will be 960 plus 160 equals to 1120 kilo Newton. So we achieved both lump mass of roof as well as for individual floor. So therefore total seismic weight of the building, that is capital W, equals to 2 into 1120 plus 960. So you will get the value of capital W as 3200 kilo Newton. So this capital W 3200 kilonewton will be helpful for us while calculating the design seismic base shear, that is VB. Now we will go for next step, that is your step number 2. We have to calculate the fundamental natural period, that is TA. Here, how we will choose the value of TA, as in given data it is not specified that it is without brick infill panels or RC frame, steel frame, or with brick infill panels. But we had given that the building is SMRF, means special moment resisting frame. So what we will do here, we will consider RC frame building with brick infill panels. So in that case, according to IS 1893 Part 1 2002, clause number 7.6.2, page 24, we have the equation as TA equals to 0.09 H upon under root of D, where we know that what is H? H is nothing but height of the building. Therefore, H equals to height of the building equals to 9 meter, 3 into 3. Now, our next step will be D, that is base dimension of the building. Remember this value. What is D? Base dimension of building in the direction of lateral load. So, your D will be 4 plus 4, considering earthquake force in x direction. So your D will be 8 meter. Therefore, fundamental natural period TA equals to 0.09 into H is 9 upon D, that is under root of 8. So you will get 0.286 seconds. So here we achieve the value of fundamental natural period, that is TA. Now we will go for next step. Step number 3. Design seismic base shear denoted by VB. So according to IS 1893 Part 1 2002, page 24, clause 7.5.3, we have the formula of base shear as VB equals to AH into W. We already calculate the value of W. In first step, lump masses to various floor level as total seismic weight of the building 3200 kilonewton. But the value of AH is still unknown for us. What is AH? AH is nothing but horizontal seismic coefficient, and AH is given by Z by 2 into I by R into SA by G. This equation is given in IS 1893, page 14, clause 6.4.2. And now, zone factor, that is Z. Here in the given data, it is the building is situated in zone 4. Hence, for zone 4, you have to refer IS 1893 Part 1 2002, page number 16, table number 2. So, for zone 4, the zone factor will be 0.24. You get this value as 0.24 from this page number and from table number 2. Now, next step is importance factor. That is I is still unknown. So, I is importance factor. And one more thing is given, that our building is school building. So, for school building, the value of I will be taken from IS 1893 Part 1 2002, page number 18, table number 6. So, for school building, you will get the value of I as 1.5. So, we got the value of Z as 0.24. We got the value of I as 1.5. Now we will go for response reduction factor, that is capital R. So here capital R equals to response reduction factor, and here in the given data it is told that the building is SMRF, means special movement resisting frame. Therefore, from IS 1893, page number 23, table number 7, you will get the value of R as 5. Now, the last value is SA by G, which is still unknown for us. So, for SA by G, I told you in the previous lecture that the value of SA by G depends upon the type of soil. Here in the given data, the type of soil is medium, and the second parameter is time period. So, this type of soil is medium, and the time period we had calculated here as 0.286. So, for TA 0.286 seconds, and for medium type of soil you will get the value of SA by G as 2.5 from the figure 2, page number 16. Now, we will put all the values in this equation, that is VB equals to AH into W. So, AH equals to Z by 2 I by R SA by G. We got the value of Z as 0.24, value of I is 1.5 and value of SA by G is 2.5. 2 into response reduction factor as 5. So after solving the above equation, the value of AH will be 0.09. We had assumed the damping as 5% as it is not given in the statement. If the damping is other than 5%, then the SA by G ratio should be multiplied with the factor from table 3 of IS 1893. We had already discussed in the theory portion. So now our next step will be design seismic base shear, that is VB equals to AH into W. The value of AH is 0.09 and the value of W we had calculated in the first step as 3200. So here value of W will be 3200. So VB equals to 288 kilo Newton. Now we have to distribute the shear at its base. We have to go for lateral load distribution along with the height as well as shear distribution. So our last step, that is step number 4, is vertical distribution of base shear. Now the design base shear, that is VB equals to 288 kilonewton, shall be distributed along the, remember this word, along the height of the building as per the equation QI equals to VB into WI HI square upon summation of I equals to 1 to n WI HI square. This equation is given in IS code 1893 part 1 2002 page number 24 clause 7.7.1, where QI equals to design lateral force at ith floor. Next step, VB equals to base shear, W equals to seismic weight of floor I, and HI equals to height of floor from base. Remember this word, from base. So Now we will calculate all these values. So lateral load distribution along with the height, and we had calculated the value of base here as 288 kilo Newton. Now the first column will be for floor level, that is first floor, second floor and third floor. Here Wi, that is seismic weight of floor. Hi in meter, that is height of floor from base. Wi Hi square, Wi Hi square upon summation of Wi Hi square. We will get the whole summation from here, Wi Hi square. Next, the lateral force that we have to calculate using the expression Qi equals to Vb into Wi Hi square upon summation of Wi Hi square. And lastly, we have to draw the shear diagram. Therefore, the shear force Vi kilo Newton. Now, we know that for first floor level, the height is 3. For second, 3 plus 3, as we have to calculate the height of floor from the base. And here will be 9. Now, we had already calculated the value of Wi in our first step. So, firstly, Wi for first floor level will be 1120. For second floor level 1120, and for third floor, that is for roof, is 960 kilo Newton. All the three values we had calculated earlier. Look here, for roof, that is for third floor, it is 960 kilo Newton. Next, for each floor, that is for first floor as well as for second floor, it is 1120. Therefore, we had multiplied here 2 for first and second floor. So we will put all these data here. So for first floor 1120, for second floor 1120, and for third floor 960 kilo Newton. So Wi square will be 960 into 9 square. So you will get the value as 77760. Next 1120 into 6 square. So you will get 40, 320, and 1120 into 3 square. You will get the value as 10080. So summation of Wi square will be 128160. So the value of Wi square we had obtained here, and the value of summation of Wi square is here. So after putting both the values in numerator as well as denominator, you will get the value as 0.606 for third floor level, and 0.315 for second floor level, and for first floor level you will get the value as 0.079. Now putting these values directly here and multiplying these values with VB, that is 288 kilonewton, so you will get 174.53. Similarly 90.72, and by using the same equation but with different values you will get the value of first floor level as 22.75. So after that we will add the design lateral flow force for all the floors. So you will get this value as 288 kilonewton, which will be equals to VB 288 kilonewton. Now we have to calculate the shear force. So directly inputting these values for third floor 174.53, and then 174.53 plus 90.72, you will get the value as 265.25, and again adding 22.75 in second floor level shear force, that is VI 265.25, you will get 288 for first floor level. So for third floor you achieve the value of lateral force as 174.53 kilonewton. For second floor level, you achieve the value of design lateral force as 90.72, and design lateral force at first floor level is 22.75 kilonewton. So you have to plot the lateral load diagram in next step, and you have to plot the shear force diagram in last step by considering 174.53 at third floor, 265.25 at second floor, and 288 kilonewton at first floor. So by this way you have to distribute the lateral forces, and as we know that for top floor the dimensions must need to be in excess. So for all the floor levels the lateral load diagram will be drawn like this, and the shear diagram will be plotted in this form. So we will see the second example and third example related to the seismic coefficient method in next lecture. Thank you.